This lecture is about how to do fast search by using inverted index. In this lecture, we're going to continue the discussion of system implementation. In particular, we're going to talk about how to support fast search by using inverted index. So let's think about what a general scoring function might look like. Now, of course, the vector space model is a special case of this, but we can imagine many other retrieval functions are of the same form. So the form of this function is as follows. We see this scoring function of document D and query Q is defined as first a function of FA, that's an adjustment function. That would consider two factors that are shown here at the end, f sub d of D and f sub q of Q. These are adjustment factors of a document and a query, so they are at the level of a document and a query. So, and then inside this function, we also see there's another function called H. So this is the main part of the scoring function. And these, as I just said, are the scoring factors at the level of a whole document and a query, for example, document length. And this aggregate function would then combine all these. Now, inside this H function, there are functions that would compute the weights of the contribution of a matched query term, Ti. So this G, the function G, gives us the weight of a matched query term, Ti, in document D. And this H function would then aggregate all these weights. So it will, for example, take a sum of all the matched query terms. But it can also be a product, or could be another way of aggregating them. And then finally, this adjustment function would then consider the document level or query level factors to further adjust the score, for example, document length normalization. So this general form would cover many state-of-the-art retrieval functions. Let's look at how we can score documents with such a function using inverted index. So here's a general algorithm that works as follows. First, this query level and document level factors can be pre-computed in the indexing time. Of course, for the query, we have to compute it at the query time. But for document, for example, document length can be pre-computed. And then we'll maintain a score accumulator for each document D to compute H. And H is the aggregation function over all the matched query terms. Right? So how do we do that? Well, for each query term, we're going to fetch the inverted list from the inverted index. This would give us all the documents that match this query term. And that includes D1, F1, and through D and Fn. So each pair is a document ID and the frequency of the term in the document. Then for each entry, D sub j and F sub j, a particular match of the term in this particular document, D sub j, we're going to compute the function G. That would give us something like a TF-IF weights of this term. So we'll compute the weight contribution of matching this query term in this document. And then we're going to update the score accumulator for this document. And this would allow us to add this to an accumulator that would incrementally compute the function H. So this is basically a general way to allow us to compute all functions of this form by using inverted index. Note that we don't have to touch any document that didn't match any query term. This is why it's fast. We only need to process the documents that matched at least one query term. In the end, then we're going to adjust the score to compute this function f sub a, and then we can sort. So let's take a look at the specific example. In this case, let's assume the scoring function is a very simple one. It just takes the sum of TF, the raw TF, the count of a term in the document. Now, this simplification would help showing the algorithm clearly. It's very easy to extend the computation to include other weights like transformation of TF or document length normalization or IDF weighting. So let's take a look at a specific example where the query is information security. And I show some entries of the inverted index on the right side. Information occurred in 4 documents and their frequencies are also there. Security occurred in 3 documents. So let's see how the algorithm works. Right? So first we iterate over all the query terms and we fetch the first query term. What is that? That's information. Right? So, and imagine we have all these score accumulators to store the scores for these documents. We can imagine they will be allocated, but then they will only be allocated as needed. So before we do any weighting of terms, we don't even need a score accumulators. But conceptually, we have these score accumulators eventually allocated. Right? So let's fetch the entries from the inverted list for information first. That's the first one. So these score accumulators obviously will be initialized as zeros. So the first entry is D1 and 3. 3 is the occurrences of information in this document. Since our scoring function assumes that the score is just a sum of these raw counts, we just need to add 3 to the score accumulator to account for the increase of score due to matching this term information in document D1. And then we go to the next entry, that's D2 and 4, and then we add 4 to the score accumulator of D2. Of course, at this point, we will allocate the score accumulator as needed. And so at this point, we allocated D1 and D2. And the next is D3. And then we add 1, we allocate another score accumulator for D3 and add 1 to it. And then finally, D4 gets a 5 because the information, the term information occurred in 5 times in this document. Okay, so this completes the processing of all the entries in the inverted index for information. It processed all the contributions of matching information in these 4 documents. So now our algorithm will go to the next query term, that's security. So we're going to fetch all the inverted index entries for security. So in this case, there are 3 entries, and we're going to go through each of them. The first is D2 and 3, and that means security occurred 3 times in D2. And what do we do? Well, we do exactly the same as what we did for information. So this time we're going to change the score accumulated D2 since it's already allocated. And what we do is to add 3 to the existing value, which is 4. So we now get a 7 for D2. D2's score is increased because it matched both the information and the security. Go to the next entry, that's D4 and 1. So we would update the score for D4, and again we add 1 to D4, so D4 now goes from 5 to 6. Finally, we process D5 and 3. Since we have not yet allocated a score accumulator for D5, at this point we're going to allocate 1 for D5, and we're going to add 3 to it. So those scores on the last row are the final scores for these documents, if our scoring function is just a simple sum of TF values. Now, what if we actually would like to do length normalization? Well, we can do the normalization at this point for each document. So to summarize this, right, so you can see we first processed the information query term information, and we processed all the entries in the inverted index for this term. Then we process the security. It's worth thinking about what should be the order of processing here when we consider query terms. It might make a difference, especially if we don't want to to keep all the score accumulators. Let's say we only want to keep the most promising score accumulators. What do you think would be a good order to go through? Would you process a common term first, or would you process a rare term first? The answer is we should process the rare term first. A rare term would match fewer documents, and then the score contribution would be higher because the IDF value would be higher, and then it allows us to touch the most promising documents first. So it helps pruning some non-promising ones if we don't need so many documents to be returned to the user. Right? So those are all heuristics for further improving the accuracy. Here you can also see how we can incorporate the IDF weighting. Right? So they can easily be incorporated when we process each query term. When we fetch the inverted index, we can fetch the document frequency, and then we can compute the IDF. Or maybe perhaps the IDF value has already been pre-computed when we index the documents. At that time, we already computed the IDF value, then we can just fetch it. So all these can be done at this time. So that would mean when we process all the entries for information, these weights will be adjusted by the same IDF, which is IDF for information. So this is the basic idea of using inverted index for fast search, and it works well for all kinds of formulas that are of the general form. And this the general form covers actually most state-of-the-art retrieval functions. So there are some tricks to further improve the efficiency. Some general techniques include caching. This is just store some results of popular queries, so that next time when you see the same query, you simply return the stored results. Similarly, you can also store the list of inverted index in the memory for a popular term. And if the query term is popular, likely you will soon need to fetch the inverted index for the same term again. So keeping it in the memory would help. And these are general techniques for improving efficiency. We can also keep only the most promising accumulators, because a user generally doesn't want to examine so many documents. We only need to return high quality subset of documents that likely are ranked on the top. For that purpose, we can then prune the accumulators. We don't have to store all the accumulators. At some point, we just keep the highest valued accumulators. Another technique is to do parallel processing, and that's needed for really processing such a large data set like the web data set. And to scale up to the web scale, we need to have special techniques to do parallel processing and to distribute the storage of files on multiple machines. So here, here's a list of some text retrieval toolkits. It's not a complete list. You can find more information at this URL on the bottom. Here I listed 4 here. Lucene is one of the most popular toolkits that can support a lot of applications, and it has very nice support for applications. You can use it to build a search engine application very quickly. The downside is that it's not that easy to extend it, and the algorithms implemented, they are also not the most advanced algorithms. Limmer or Injury is another toolkit that does not have such a nice support of application as Lucene, but it has many advanced search algorithms, and it's also easy to extend. Terrier is yet another toolkit that also has good support for application capability and some advanced algorithms. So that's maybe in between Limmer or Lucene, or maybe rather combining the strengths of both. So that's also useful toolkit. Meta is a toolkit that we will use for the programming assignment. And this is a new toolkit that has a combination of both text retrieval algorithms and text mining algorithms. And so topic models are implemented there, and there are a number of text analysis algorithms implemented in the toolkit. as well as basic search algorithms. So to summarize all the discussion about the system implementation, here are the major takeaway points. Inverted index is the primary data structure for supporting a search engine. That's the key to enable fast response to a user's query. And the basic idea is to process pre-process the data as much as we can, and we want to do compression when appropriate, so that we can save disk space and can speed up I/O and processing of inverted index in general. We talked about how to construct the inverted index when the data can't fit into the memory. And then we talked about the fast search using inverted index, basically to exploit the inverted index to accumulate the scores for documents matching a query term. And we exploit the zip slaw to avoid touching many documents that don't match any query term. And this algorithm can actually support a wide range of ranking algorithms. So these basic techniques have great potential for further scaling up using distributed file system, parallel processing, and caching. Here are two additional readings that you can take a look at if you have time and you're interested in knowing more about this. The first one is a classic textbook on the efficiency of inverted index and the compression techniques, and how to in general build an efficient search engine in terms of the space, overhead, and speed. The second one is a newer textbook that has a nice discussion of implementing and evaluating search engines.